All right. Thank you so much for having me. I'm really delighted to give today's talk about designing cameras in an end-to-end fashion to detect what I call the invisible. That is imaging and computer vision in harsh conditions. So today's imaging and vision systems surround us in our daily lives. We use these in our personal devices, in health and robotics, and in our self-driving vehicles of today or of the future. But to build really robust vision systems, we must handle edge cases. Edge cases can not only be the edge cases such as classes that are really seen, but for example, also weather conditions, as shown here, dense fog, where I'm showing you a histogram or a capture campaign done in Northern Europe, where we captured a very small amount of ultra dense fog. And it is challenging to use supervision of existing supervised models to tackle all of those edge cases, just because these cases are very rare and you need a very massive machinery to capture those cases. And also, we want to make sure that we handle those edge cases not only for one specific camera system, where we maybe have the ability to build up a very large system, very large training loop that allows us to capture, re-annotate, have some active learning in there, do that for one particular system, for one camera generation, but also do that for different cameras for diverse applications in the world. So let's have a look at one specific harsh case. And this is a harsh case that doesn't even happen that harshly. That is just nighttime imaging and computer vision. Here you see an example of the captures that today's vision systems and autonomous vehicles have to handle. In this case here, we have very low contrast around object discontinuities, lots of ambiguity in the scene, but also lots of ambiguity introduced in the ISP, in the post-processing, in the sensing itself due to HDR capture conditions that we have to handle here. So it is not really only the scene that we need to be worried about. It is, in fact, the whole chain, all the way from photons emitted from some source in the scene or the vehicle itself, all the way down to an image or perception output. So here's a typical imaging chain that could be found in a self-driving vehicle, for example, where light enters the scene, is focused through some optics on the sensor, which digitizes the light and gives us a digital reading that we then process in a relatively complicated cascade of individual processing blocks in the so-called image processing pipeline, the ISP. That spits out an RGB image that you can then feed into a downstream neural network to perform object detection, for example. And so, as I said, today, all of the edge cases that happen anywhere in that signal chain can happen in the scene itself, in the optics, in the ISP. All of these edge cases are really handled in the downstream neural network using supervised training. We know that that works. That is a good approach, but it doesn't really solve the problems where they happen. So the best practice is to use supervision to handle the edge cases. And that is not only because that is the most successful approach, but because the downstream neural networks are differentiable. So we can actually add training data that covers those edge cases and then have our model learn to cover those edge cases. The earlier blocks in the signal processing chain, the imaging chain, are not necessarily differentiable. So we have ISPs that are not differentiable, sensor designs that are not differentiable, optics that are not differentiable. The scene itself is also not differentiable. So this makes it challenging. And so we have in practice to manually design those blocks that are essential in an overall vision system. And this is done today by golden eye experts in months and months of hand tuning. For example, if you take the ISPs and their parameters as an example, then those experts design with a lot of domain expertise those blocks, make them perform good with respect to traditional image quality metrics oftentimes, and also sometimes visual inspection. So those blocks are manually designed, and it does not necessarily mean that they're optimal for computer vision applications, such parameters object detection here. And this really goes for all steps in the imaging and vision stack. So in this talk, I'll show an approach how we can take those blocks here, the ISP, for example, make it differentiable, enable us to optimize the weights, the parameters, the processing itself to perform better and to tackle those edge conditions, edge scenarios where they're oftentimes generated, where the ambiguity is oftentimes generated in the earlier layers of the camera pipeline and in the scene itself. And I'm also going to show how we can do that even further down the line in the optics, how we can design customized optics, can really build an end-to-end system that goes all the way from photons in to detection out and optimize the entire camera stack here. And even going one step further, I will show you how we can represent the scene with a differentiable model and then think about completely different new ways how to do object detection and inference, for example, by matching an observation as an optimization problem. So let us first dive into ISPs. So I want to look at a computational camera pipeline that optimizes an ISP for the edge cases. So we can at least rule out the edge cases that are introduced in the ISP itself. So an ISP, as I mentioned before, contains many complicated processing blocks with a large set of discrete and continuous parameters. And these blocks are oftentimes not differentiable. So how do we make it differentiable? This works in two steps. We first learn a differentiable proxy function, an approximation of the underlying ISP that mimics the ISP. So it takes as input raw images, raw sensor readings, and outputs an RGB image. And then we take that proxy network and we fix its weights, and we can then backpropagate gradients from a loss function that may be defined on the image or a downstream neural network all the way back to the parameters, the inputs of that proxy network. So we can solve it as an optimization problem. So let us first look at how we learn this differentiable proxy. So consider a black box function that is our ISP that takes as input raw input images and parameters, the individual ISP block parameters that affect the behavior of the ISP. Then what we do in order to generate a training data set that we can use in order to mimic this ISP is sample the parameter space of input parameters of this black box function. That gives us a training data set of parameters, an input image, and outputs of that black box ISP. It can be a hardware ISP, software ISP, it doesn't matter. Now what we do is we take a relatively standard image-to-image network, a UNet with some minor modifications that takes as input the parameters and the input image itself. And we generate then, we optimize this network to have the behavior that we intend with this particular network, that is to reproduce the behavior of the ISP itself, depending on input image I and a set of parameters P. So now once we're done, finally training our network on this training data set that we generate from the hardware ISP, we freeze the parameters of this particular network, and we keep it then as a function that mimics our ISP. But now the nice thing is this is a differentiable function that we can use to optimize the input parameters. And this is the second stage. So we take this fixed network and it takes input the parameters, the particular raw image that we're interested in, and then we place a loss function on the output of that particular proxy ISP. Let's say, for example, we have a perceptual loss, a loss function that is defined on the output of the ISP, and a reference output, a specific target value that we want to achieve, for example, from simulated data. Then what we can do is we can take that task loss and backpropagate gradients from the task loss through the fixed neural network all the way to the input parameters, find us the optimal parameters that perfectly represent our target image, minimize our target loss function, and solve a black box parameter optimization as a first order optimization problem using existing optimization algorithms, stochastic first order optimization algorithm. So now how do we use this machinery to go further and do joint image processing and detection, for example? So a relatively naive approach is to take a fixed neural network, a downstream neural network, an object detector, for example, faster RCN, and concatenate that with our proxy. And then we have an end-to-end pipeline that itself is differentiable. We can define an IOU loss on the outputs of the object detection network, and now backpropagate the gradients all the way to the input parameters of the ISP. Optimize optimal ISP parameters for that particular IOU loss that we're interested in. We can even go one step further, and we can include the parameters of the object detection network itself in this optimization, slightly change the optimization up so that we can use different learning rates, do some tricks about the learning schedules, but in the end, we can basically optimize for both the ISP parameters, hardware ISP parameters, as well as object detection network weights. And this is an approach that works extremely well. So even on a small data set, just to show some cool qualitative examples, we've been able to outperform state-of-the-art stacks that have been deployed in the wild. For example, here we reproduced object detections on a Tesla autopilot stack that we reverse engineered, and you can see this version of the autopilot stack. Folks were relying quite heavily on radar. There's quite some flickering in there in the detections, and we can do really well even with a relatively small data set and use pseudo raw data input that came from the cameras here. Even though we don't have quite the amount of training data that the Tesla has available, large machinery that's built around it, we have benchmarked against them and achieve substantially higher AOU values on relatively large data sets that we captured and manually annotated. So here's an example, a very different sensor, an AR231, that has a different color filter array under harsh conditions, just mounted randomly behind the windshield. And you can see that handling completely different cameras, different conditions can be done very efficiently with this approach because we train all of the parameters jointly here, all the way from the low-level image processing blocks to the downstream neural network. Here's another example in extremely harsh weather. And here you can see that image processing approaches jointly with downstream detection can certain issues that we have. Multi-sensor setups, for example, LiDAR, which becomes completely unusable because of the heavy backscatter. So just a few examples that show you that this is a successful approach to overcome key challenges in vision systems. So let's go one step further down the chain. Let's look at how we can optimize optics together with the entire stack, together with the ISP, with the downstream neural network. So today's optics design is done manually by manual optical design tools such as ZMax or Code 5. Here you see some of those guys, some of those imaging and optics experts that optimize really elaborate optical systems and can do well in these traditional tools. But key thing here is really that they're optimized in isolation for traditional compartmentalized loss functions and metrics such as spot size, without consideration of a downstream network or an application. These modern tools are really awesome in the sense that they have a huge library of individual designs that optics engineer can rely on, different that features different materials, all kinds of different applications for these optics, and they're really easy to use these days. But as mentioned before, one of the big downsides is that we cannot really easily backpropagate gradients through the optics. We cannot design the optics jointly with a computer vision stack. We overcome this by building, again, a proxy model, differentiable modeling of the point spread function, here in this case, especially varying point spread function that we trace here through an optical system, by modeling these PSFs, which describe the optical system, with a neural network as a proxy function for Zemax or Code 5 itself. And so what are the optical design parameters? It can be individual radii, surface descriptions, description parameters, can be different spacing parameters, different material types. All kinds of different parameters can affect these optical PSFs, which describe the characteristics of the overall optical system. So now what we can do is, in a similar approach like before, we can consider parameters, these parameters that I just mentioned, and we can generate a data set using Zemax forward ray tracer black box function, as far as we're concerned, produce outputs that we can use for training. And here's our PSF generator network, which generates a PSF at a certain field and a vignette factor. And what we have here as an architecture is, and we can define the loss function to optimize that network, but what we have here as an architecture is a network that consists of an MLP and a convolutional decoder to produce those output PSFs. And as before, we can learn the weights of this network, the proxy Zemax, if you want so, by sampling through different parameter settings, and then using this as a training data set, optimizing a loss between the PSF, the vignette factor, and the ground truth simulate forward model with the complex Zemax ray tracer, and finally fix this model. Then again, what we can do is similar like the ISP optimization before is we can optimize for optimal PSFs. In this case, we can optimize for tiny spot size here. And you can see here the result of the optimization of the parameters, so gradients backpropagated all the way through the to the individual input parameters of the optical system. And we can do well and design an optical system in this end-to-end fashion. So we have validated this approach and built actually several optical systems for natural imaging, for display purposes, object detection, and traffic light detection. And each time we get a different optical design tailored to the domain-specific use case. So what we have here in this first case is an optical design that is optimized for natural image capture. And what we can see here, if you look at the sort of middle fields, that we get a design which has a much narrower tail, so we don't have such a long tail than the nominal design. And the nominal design, by the way, is a design which in this case here was designed for over 2 months by optics engineers that are trained to do this, find the best design, and tweak all the Zemax parameters, optimizer parameters in the best fashion. And this is what they came up with. We find a very different design. In this case here, what you can see here is that it has a larger F number. So we get a little bit less light efficiency through this one here, slightly peakier PSFs, and we can handle that on the reconstruction side fairly efficiently. In the ISP, it gives you slightly more noise in low light conditions. We can still recover that, but the overall sharpness here is drastically improved if we jointly optimize this together with our hardware ISP. We get a better output, which is visibly better here in this case. We get again yet another different ISP if you were to optimize this with a neural network, for example. Now let's have a look at automotive object detection. Entirely different PSF here. What we get is a very uniform behavior of the PSF, especially in the blue channel, and larger PSFs than the nominal design. And you can see that this actually improves detection quite substantially, although we get slightly more blur. In this case here, the F number is actually lower. So we do want to make sure that we get more light here in this design for object detection. And we can, on average, do substantially better. Here is the last example where we have a traffic light detection, so small objects at the periphery of the image. You can see here that for 6 degrees and 8 degrees, the overall extent of the sort of core tail of the PSF, which contains most of the energy, is contained to a smaller set of pixels, so you get less blur for those regions, and that helps to detect those small traffic lights. Here's a qualitative example, and you can see here that we detect substantially better. In all cases, we've done a quantitative evaluation, detecting up to from 5 to 10% improvement in mean average precision for these scenarios. So now I want to look at sensors. We've looked at the whole chain from ISPs to optics, but I haven't talked about the sensors. How can we use sensors and a smart design of novel sensors, robust new sensors, to overcome some of the challenges that we have in the edge cases that we talked about at the beginning of the talk? So let us have a look at a scenario like this one here in harsh weather, where we have a lot of backscatter affecting severely the LiDAR measurements. Here the first response is reported, and at the same time we have a lot of scattering that we see in our RGB capture, in this case here stereo capture. We can gate out some of these backscattered components affecting both stereo and LiDAR sensors by devising a new sensor that gates out some of these contributions. Gating works as follows. We send out a pulse of light, and we only record light that comes back to the sensor at the given time. Here you see 3 gated slices at 3 different temporal offsets, 3 different temporal gates that we capture in the scene. And you can see here that in the first slice, we have gated out all the far components, path with very long path lengths. In the second slice, we've gated out early components and long components. In the last slice, we've gated out everything that's early. So that allows us to gate out certain path of the light transport in the scene. We can take the sensor, bolt it on a vehicle, and it becomes nothing else than a simple gated camera source, diffuse flash laser source that can mount here below the bumper, and we add a camera behind the windshield. We can devise a 3D object detection architecture that uses these gated images in a very nice fashion. You can get 2D proposals out of these gated images because they're very high spatial resolution, other than existing LiDAR measurements. They are basically at the same resolution of RGB camera sensors. And at the same time, through the variations of the intensity in the gated images that we capture, we have depth encoded. So they also have a direct encoding of depth at this high resolution. That can be used and get really nice 3D object detection results. And it works well in harsh conditions. Here you see an example of a night capture, which is challenging for conventional RGB pipelines and stereo pipelines. And the proposed architecture works quite well here using these gated images. I can show you an outdoor image here. There you see color-coded the 3 individual gated slices in red, green, and blue. And here's some more harsh cases in dense fog. And again, completely different image modality. Here we use a very tiny data set, 10,000 samples to train this network. But for fog, even at long distances, this approach gives robust object detection results. Another scene for fog. You see some pedestrians that are actually there on the side of the road. Here, an overland drive, also very challenging. Not much you get in the RGB captures in this case, which are not shown here, by the way. But you can get nice results with very long distances, which is in very, very sharp contrast to LiDAR measurements, which do not work in these cases due to backscatter, and they have a low resolution at long distances because of the angular scanning approach that these LiDAR scanners are using. Now, another thing that you can do with this new sensor modality, images, is train other models. For example, a model which we call zero scatter, which takes as input RGB images, so affected by the haze and the scatter in the scene, and produce images that have this scatter removed. So how can we dehaze, defog, desnow these particular scenes, these RGB scenes, using a neural network? We can do that by using gated images as a loss function. We can, on the resulting images that a dehazing network produces, define a loss that simulates gated images, and then measures the difference to the actual gated image, uses this as a loss function to train the network weights of this dehazing network, which works because these gated images are not affected as much as other modalities by the backscatter in the harsh scenarios. Here's an example what this accounts to, and you can see here that especially for long distances, we can get really good dehazing results with this approach here under challenging conditions. These are all unseen scenarios, of course. Here's an example in fog that shows you that you can do quite a bit with this approach as an indirect way to supervise our existing image-to-image models. So far I've talked about different approaches that tackle the whole camera and vision chain, all the way from photons in to the optics, through a particular sensor, different sensors, through the ISP, through a detection network, to an output of that particular detection network. But what I haven't looked at so far, and what I alluded to at the beginning of my talk, is the scene itself. So how can we reduce ambiguity of the scene by making the scene differentiable itself? And this is what we're going to do here in the last portion of my talk, which introduces the concepts of so-called neural scene graphs that we can use for inference and data generation. Let us look at a dynamic automotive scene, such as this scene here. It's just a scene from the Kitty dataset. If you take a frame T at a given time, then what we propose is to model this entire scene with an implicit scene representation that is based on scene graphs. So what is a scene graph? We consider all the dynamic objects in the scene, all of the vehicles here in this case, then they're all the nodes of this particular scene graph. A scene graph is nothing else than a directed acyclic graph. And at the edges of that particular scene graph, we have transformations that transform the objects to their particular positions in the 3D scene. Such scene graphs, seemingly very simple, are a very well-known concept in computer graphics, have been explored there for a while to model complex compound scenes that consist of many different objects. So how do we represent this entire scene? This image here, just an array of pixels with a scene graph, an implicit neural scene graph. So we first take out one specific object here. Let's, for example, take the truck here of interest, and that now is a node of the particular scene graph. We assume that we have, let's just assume we have its bounding box comes from a tracker, for example. And what we can then do once we have a transformation of the bounding box in the 3D scene is that we can shoot a ray from our camera through this bounding box. And at every location that we sample the bounding box, different sampling schemes that we explore, we can sample the radiance, which we represent with an implicit neural radiance field, representing this particular truck object. We can collect the radiance, can integrate it, and then we get only the radiance that is reflected from this particular point on the truck. And we do that by introducing one model for all the trucks and all the vehicles. That is one implicit model for all of the objects which are from the same class, for example. So now, what do we use in order to represent the radiance? We use a neural radiance field, a nerve, super popular neural rendering approach. And what we do here is, instead of using a typical nerve here, we implement it as a two-stage model where we give not only the location, the direction that we want to sample the radiance in, but also the location of the particular object, P here in the global scene, and a latent code. Latent code encodes differences between the individual object instances that we represent with our model, and the position that we input here, P here in this case, makes sure that we encode global illumination effects depending on the position of the vehicle or the object that we want to represent in the scene, depending on the position where it is in the scene, depending on the illumination. So we add these two inputs to a conventional nerve that outputs color and opacity at every given location that we sample it at, and then we integrate those along array. So now we can do that for all objects in the scene, define them all as individual nodes with shared models. We use a few separate models for trucks and cars, then encode these individual models with their latent codes that we optimize for during the training time, and then generate pixels by accumulating the radiance for all of these individual dynamic objects that we have in the scene. So all of the dynamic objects are now handled by individual modified radiance fields that we model in our scene graph. Now, what I haven't talked about so far is the background itself, the static background that does not change. For that, we just use a plain nerve, but we sample it in a slightly different way. So there are scales. We just use a set of planes, multiple planes that we sample this particular nerve at to get background components, static components in the scene that do not move. Then finally, we have a full array representation of the radiance through the scene. We take all of the samples of the dynamic objects and the static background objects and integrate them, which gives us a final image here. So this is the final nerve, gives us the full image that we now represent. So now if you want to represent a different frame of the same scene here, all what we have is we move these individual node representations around, keep the background as is if we don't move through the scene, and evaluate there again at a different location. So all of a sudden, we have an implicit neural scene representation that allows us to modify scenes and change scene arrangements, scene configurations, generate entirely new scenes. And I want to show that here. So for example, we train our neural scene graph representation on a few videos from the Kitty data set. Then we can add trucks, move them around, put them at different locations, rotate them slightly. And all of this is consistent with global illumination cues, allows for occlusion and realistic rendering. Here's an example of global illumination effect. You see the highlights move along with the vehicle being moved. This is encoded in our particular scene graph representation. So obviously, like regular nerves, we can also move into the scene and change object locations in the scene, change our ego location, and simulate entirely different scenarios of these captured learned scene representations. Finally, once we have such a representation, we can use this for inference. We can take a scene graph and optimize it so that it matches an input image. So how do we do that? Let's say we have this as an input image, here the ground truth bounding boxes are overlaid from the kitty data set. Let us assume we have a neural scene representation, neural scene graph as described. Then what we can do here is, so here we start with a sample of this particular neural scene graph, somehow initialized with different approaches that we have explored. And then we optimize this scene graph to produce as an image that is as close as possible to the input image just by optimizing the latent codes and the transformations of the individual nodes. And that gives us a representative image of that scene and an entirely different approach how to do object detection. We can obviously also use neural scene graphs to generate very large training data sets of pseudo-simulated data and train feed-forward networks to do object detection or other perception tasks on these relatively large data sets. So in summary, I've shown you a number of approaches that tackle edge cases, the harsh cases that we have to handle in perception systems by designing systems in an end-to-end fashion, particularly looking at the entire camera chain, including post-processing, sensors, optics, and the scene itself. And I'm convinced that such perceptual cameras will allow us in the future to overcome a lot of the challenges that we have with today's supervised training approaches, especially when we're at the point where we can generate large data sets of pseudo-simulated data with neural rendering approaches. We're at the stage where we can use these to train our existing models and can generate conditions which are otherwise difficult to see. So more decomposable, interpretable networks handling the edge cases exactly where they're happening allows us to achieve some of these scenarios, which are in fact superhuman vision capabilities, such as seeing in fog and snow and other challenging conditions that for us as humans are sometimes unsolvable. So with that, I'd like to thank you all for the interest in my talk, and I'd like to highlight that some of the results and papers that I've mentioned are all on my webpage, which is shown on the title slide and this last slide here in the slide deck. So with that, thank you all.